So Professor Chris Baxter is a professor at Rhode Island, University of Rhode Island. He's head of the department there. So is this okay, Chris? Yeah, there you go.
Good morning, everyone. Thank you to Kenichi and to the entire Geosystems group for inviting me. I'm one of the Virginia Tech representatives. Sometimes I feel a little bit like, the cousin that showed up at a family reunion that nobody knew about, certainly in a crowd like this, but we are proud alumni of Jim's legacy. And so I am thrilled to, along with my friend and colleague Russell Green, to represent Virginia Tech here. I'm a little nervous. Being asked by Kenichi to talk about fundamental soil behavior and Jim's contributions that is not a small task in 18 minutes or whatever I have time for. But I'm going to give it a shot anyway. And I'm going to be very specific about some of the work that Jim did and that I was involved with quite a long time ago. Just as another brief introduction, so I'm a professor in the departments of ocean and civil engineering at the University of Rhode Island. I've been there about 25 years since I graduated from Virginia Tech and have loved every moment of it, but haven't worked in a lot of these areas in a while. My career sort of headed off in a different direction. So this has been a very enjoyable experience preparing this talk, so I'm really honored to be here. And I will start with a couple of short stories, if you'll indulge me. The first one is when I graduated from Virginia Tech in 1999, I decided to take a postdoc at the University of Rhode Island in their ocean engineering department, instead of accepting a faculty position at another university. And I talked to Jim quite a bit about this bird in the hand versus two birds in the bush, as Jim, I remember Jim mentioning it. And it turned out to be a wonderful opportunity, but I was quite nervous about heading off into a different field. And during my year-long postdoc, I was invited to an NSF workshop on the West Coast dealing with submarine landslides, which is the area I had been working on. And I was honored to, even though I was sort of new to the field, I was honored to go. And it turns out Jim had been invited to give a keynote discussion at this workshop. And unbeknownst to me at the time, when Jim had been invited, he said, I will accept your invitation if you also invite Chris Baxter. And I found that out much later. And I was just struck by Jim's generosity and how he was always thinking, he always looked to the future. He was a very forward-looking person, but he always helped us out along the way when we needed it. And I'm forever grateful for that and many other things. So that's my first story. My second story is one when maybe the second time I met Jim. I specifically went to Virginia Tech to work with Jim Mitchell. Of course, I had read his papers, and I met him once at a conference and asked him a question, and I knew I wanted to work with him. So I went there specifically to work with him. And I was very fortunate to be granted a teaching assistantship as part of his startup package. So that was a great thing for me. And I clearly remember the first meeting we had. So I show up at Virginia Tech in Blacksburg. We sit down for our first meeting, and Jim says, we have a really unique opportunity here. I have funding for you through my startup package. We can work on whatever you want. What are you interested in? And I said, well, I came to Virginia Tech to work with you. I'm very interested in ground improvement. I had been working on some ground improvement projects in my consulting experience. And so I would really like to work on some ground improvement topics. And he said, you know what I'm interested in? Aging of sands. And I quickly said, I am also interested in aging of sands. And it turned out to be a great opportunity for me because, among many things, it was one of his favorite topics, certainly when I knew him, and to work on something that he was so interested in and passionate about meant I had a lot of access. So I'm going to talk about aging of sands, and the title of my talk is A Continuing Enigma. This is something, as I mentioned, Jim was very interested in. We worked on it for a long time. He worked on this with many other people as well, including Christine Human before he came to Virginia Tech. And so I'm gonna talk a little bit about one of his favorite topics, I think. And I shamelessly borrowed this title from a title of a paper that Jim wrote in 2008. He was asked to give a keynote lecture, and he wrote this paper called Aging of Sands, A Continuing Enigma. And so what I really wanted to focus on is, I was very excited when this paper had come out. I had already been working in Rhode Island for quite a while, and so I was like, has Jim cracked the code? Has he figured it out? And so I read this with great interest, and I'm going to skip to the conclusion section of this paper. And he has a section, I'd like you to look at this. It says, his first conclusion is aging of sand and the associated improvements in stiffness, penetration resistance, and liquefaction resistance are ubiquitous among freshly deposited and or densified deposits of silica sand. And Russell Green and I have laughed many times about this word ubiquitous, because for those of us who have studied aging of sands, it is a hard nut to crack, and it can be a very elusive phenomenon. So I might object to the word ubiquitous, meaning everywhere, or certainly somewhere where you could see it in a lot of cases. And if it is that, then why is it so difficult to study? But anyway, Jim was always the optimist, and he saw aging of sands in lots of places. So that's the context of my talk. With that, let me just tell you how briefly I'm going to talk. I'm going to talk a little bit about time-dependent properties in sand, or aging of sands. I'm going to say how difficult it is to reproduce, either in the field or certainly in the laboratory. We'll talk a little bit about the underlying mechanisms. And I think one of the exciting things that I wish Jim were here for is, I think there has been a lot of development in this area in the last few years, and I think we're close. I think we're close to really understanding this phenomenon a lot better, and we just maybe need a little bit more work in the field to really characterize this well. And then I'll finish with some concluding remarks. And so I'll come to that. So, where should we start? Let's start at the beginning. Let's start with Mitchell and Solomar. One of Jim's great attributes was he always seemed to be at the beginning of a trend, of several trends in his career, right? His work on clay mineralogy was a predecessor to geoenvironmental engineering. His work in ground improvement was in the early stages of that tremendous field. And when you look at aging of sands or time-dependent properties of sands, there was a couple of studies earlier than this, but this is the study that really started it all. And it was time-dependent strength gain in freshly deposited or densified sands. So let me tell you what the problem that Jim and Solomar identified as associated with the Jebba Dam project in Nigeria. So we're looking at a couple of figures, looking at either blast densification on the left or vibrocompaction on the right. And this is the classic aging of sand type figure, where you might have a CPT profile before densification, and then immediately after densification, despite ground settlement, measurable ground settlement, measurable increases in density over the site, you might have a sometimes significant decrease in penetration resistance. But then over time, the idea is, and some of the evidence has shown, that you can get significant increases in the weeks and months that follow. And on the right, you can see a similar thing following vibrocompaction, where in this case, there wasn't a large decrease in penetration resistance following vibrocompaction, but it really kind of smoothed out the dense and loose spots. But then with time, again, you see this increase in penetration resistance. And so I think this really started a great interest in aging of sands, and in particular, aging of sands associated with ground improvement. However, we do see these time-dependent effects in lots of things. I could show several slides of liquefaction resistance or other things, but aging of sands, really, we could look at increases, and they're well-established increases in small strain shear modulus, So this is some of the work that I did for Jim for my PhD, just looking at increases in small strain shear modulus with time, electrical conductivity, liquefaction resistance, there's lots of evidence there, stiffness and shear strength. This one is a really very interesting figure that makes me think of a lot of things. This is a researcher from this is Daramola, 1980. Sort of if you like this field, a lot of people go back to this figure, which shows, it's hard to see from this angle, but over the course of like 150 days, sort of a clear increase in stiffness that's occurring just in consolidated drain triaxial tests. I will say several people, including myself, but I know several groups that have tried to reproduce these results, and it's tricky, surprisingly tricky in the laboratory. And so it would be one of the challenges in our field, as we all know, is it's sometimes hard to reproduce results. We often do a study, publish it, and then move on. And we're not so great about reproducing results. And I would argue this is a challenging, if anybody has data that has reproduced that, I would love to see it because I have not seen it. But anyway, these are the trends that we look for. And of course, penetration resistance, increases in penetration resistance with time. Where do we see aging effects measured in the literature? We see them in hydraulic fills, and we see them sometimes following ground improvement. And this is the big promise or the potential of aging of sands, is following improvement techniques like dynamic compaction, vibrocompaction, blast densification, and sometimes in the laboratory. And I just wanted to highlight a really wonderful study from Chuck Dowding and Roman Ritsu. This was a laboratory study soon after Mitchell and Solomar came out, and where they basically had a tank. They pluviated sand in the tank, set off charges, and then you can see they measured penetration resistance. This is the increase in point resistance versus time with distance away from where they blasted or set off charges in the center. And you can see they got increases with time just sitting there. They got big increases depending on the types of charges they used and so on. So again, this is some really nice evidence of aging effects in a controlled environment. But most of our stuff comes from the field. Now, I will say, despite that nice promise of these increases with time, there's also a lot of evidence where, not a lot, there's some published evidence where no aging effects have been observed. And so, unfortunately, I'm showing some of my work. This is some laboratory studies showing penetration resistance versus depth in smaller scale experiments, things that are aged over time, loose and dense, different temperatures, different pore fluids, and we saw almost no time-dependent increases. And then here's a field study from some work done at Michigan with my friend and colleague Russell Green, and there's others. There are other studies, but this was a blasting experiment where you can see some pre-blast CPT, and then they did a very well-controlled study following blasting, and in that case, they did not see increases with time or significant increases with time. I highlight this, not to pick on me or anybody else, but I think this is one of our challenges in academia, and in that we don't like to publish negative results. In fact, just a 1-minute tangent, I like, there's a certain podcast that I like called Freakonomics Radio, and they have just put out a series on academic fraud in the social sciences, not in engineering. And one of the challenges they cite is that people are not encouraged to present negative results. You know, you have a hypothesis, you test it, and it seems like the only things that get published are when it works. And I think in a particular problem like aging of sands, this would be an area that is really needed, where we need to see when it works, when it doesn't, why didn't it work, because I think that would help solve the problem. Anyway, so that's, get off my soapbox there for a second. So let's talk a little bit about these mechanisms. I'm not going to spend a whole lot of time on these because I just wanted to introduce this subject and talk about Jim for a little bit. But Mitchell and Solomar, and in particular in the 2008 paper, Jim highlighted these 4 mechanisms, actually mostly the first 3. Again, very interesting from the weight of Jim's reputation. So in the literature, if somebody's doing a study on aging of sands these days, typically they say, yeah, one of the dominant theories or hypotheses is that it's chemical. There's some chemical effects going on. There's some dissolution precipitation reactions going on. And they always cite Mitchell and Solomar. Despite the fact that Mitchell, I think Jim, pretty clearly realized that maybe that's not it. But people still cite that. Microbiological processes, I'm actually not going to talk a lot about that. My colleagues Ed or Jason can talk a lot about biological effects, but I think in the time frames we're talking about, maybe biological effects may not be as significant. And then I'm going to focus on these last two, the physical processes, which I think are really, there's been some recent work that is really getting us closer to the answer, in my opinion. 1 second on the chemical side. This is a really, really nice study. I enjoyed reading this paper a long time ago, and I enjoyed rereading it by some colleagues in Canada from Yoshi et al. And they did a really intricate laboratory study where they had these rigid wall cells. They had these little penetrometers that they could push at different times, very tiny amounts, and they just weighted over time. And you can see here they published this result where they said, yep, there's this clear increase with time over the course of a year, and they said, aha, there's aging, and then they did a whole bunch of scanning electron micrographs, and they said, oh yeah, that's unaged, and it's really hard to see here, but they found all sorts of what looked like precipitate, gluing the particles together, and they said, aha, we've got chemical stuff going on. And again, this gets back to, it would be really nice if we could reproduce these results, but I know several groups have tried to do this and have not seen similar results. Either with the precipitate or certainly the increases in time. So really nice study. They were pushing chemical mechanisms, but I've not seen in the 30 years since anybody be able to reproduce these results. So I think this is probably not the dominant theory anymore. And I wish people who did a quick literature review would recognize this. On the mechanical side, really, it goes back to Schmertman in the early 90s, Mesri in the 90s, and then there was some very nice work by Elizabeth Bowman and Kenichi in 2003 that looked at particle rearrangements and how that might affect either stiffness in the lateral direction or increases in horizontal effective stress. And I think the challenge with those studies was they were not able to, in my readings, go from measurable particle rearrangements to how do we get a 50% increase in penetration resistance after 3 weeks or 4 weeks. There was always a bit of a disconnect between what's going on at the micromechanical scale and these macro effects. And then more recently, Radoslaw Mikulowski and his student at the University of Michigan had this really nice idea of static fatigue. In fact, I found out about this because Radoslaw, being a true gentleman, started emailing me and telling me all the mistakes that I had made during my dissertation, and I was like, and I was just glad he read it, but anyway, in the course of that discussion, they came out with this study, and essentially said that he could try to explain the immediate decrease in penetration resistance following ground improvement or following liquefaction by essentially a decrease in the horizontal effective stress, and that with time, due to this concept of static fatigue where the particles, there's some micro crushing, and that crushing brings the grains together and the stiffness increases rapidly. And that stiffness increase translates into an increase in horizontal effective stress, which of course we know influences the penetration resistance significantly. So there was this concept of, I think I've already said that, and he showed some really nice scanning electron micrographs of grain-to-grain contact that shows this crushing, and if you stare at these long enough, maybe you could see some crushed particles here and here that he said could explain this static fatigue concept. And then just to round it out with the blast gas mechanism, so I had talked about Dowding and Ritsu's work in the 80s, and then I think most recently, Aaron Gallant who's at University of Maine, and his group have done a lot of really nice work looking at dissipation of blast gases and the effect it can have on horizontal effective stresses. And I think that explains a lot of what we might observe. So I think these last two mechanisms are really getting there. And just as a placeholder, these are some pictures from Radoslaw Mikulowski's work showing that following liquefaction, you might get a decrease in horizontal effective stress. That could explain the decrease in penetration resistance despite observed densification, load chain development, and then with time, due to this static fatigue, increases in horizontal effective stress that could translate into increases in penetration resistance. And he supported this with some discrete element modeling work, some very nice work. And I think the last piece of the puzzle would be to do some controlled field work to verify this. But again, it can explain a lot of what we see or what we saw in Mitchell and Solimar. Okay, so I'm just going to wrap it up. I still think, and I think Jim would be happy to talk about the fact that aging of sands is still an enigma. It might be ubiquitous. In other words, we might see it everywhere, but it is still extremely difficult to measure in the lab and in the field. But I do think we're getting close, and I think Jim would be excited about the work, particularly that's coming out of Aaron Gallant's group, to explain some of these effects. So we might not be there yet, but we're getting close to understanding aging of sands, in my opinion. And with that, I would say thank you very much.
Thank you very much, Chris. I'll now pass to Professor Catherine O'Sullivan. She's a professor at Imperial College, and she'll talk about the next edition of the book. So, Catherine, do you want to go?
So good morning, and thank you very much to Kenichi and the organizers for giving me the opportunity to talk about the next edition of the book on fundamentals of soil behavior. Now, when Kenichi suggested that I could potentially do this, I thought it was very daunting. So I actually relied on how my son has to approach his essays, he's 9, every weekend, where in his planning he has to do a how, why, what, when, where. And I thought that's probably a good way to do it. So I'm going to talk a bit about what the book is, why it's important, and how the 4th edition developed, and then some final perspectives. And what I'm hoping to do is I will be going over ground that is very familiar to many of you, but maybe I'll stir some memories and provoke some discussion in the later panel sessions. So what are the fundamentals? So we could think about it at a continuum or a macro scale and say it's about how does soil behave? Or in particle mechanics, which is kind of my research home, we want to look at why it behaves as it does. And then if we listen to what Jim said in his interview with Rhode, he said what we're doing in fundamental soil behavior is digging deeper into what soils are and why they do what they do. And that's a paraphrase from that interview. And the book started, as I understand, in the early 1970s. And in his interviews, Jim explained that he had a graduate class, he had some notes, and there wasn't really a textbook to accompany this class. And then he had a sabbatical period, and that seemed like a good opportunity to start to write a book. And then it was revised in the 1990s, and that's when the edition that I first came upon, and these are the first page of my notes from the CE 274 class I took with Nick, and he recommended we go and get this book, so I got a second-hand edition of it, and I can still remember opening it up and thinking, oh my goodness, this is a completely different way of thinking about soil mechanics, and it's refreshing and it's exciting, and there's so much potential to use this. So I think it was the book in my master's period here that had the biggest impression on me, and that's probably why I've ended up going down the road I went subsequently with John, looking at how we can model soil at the particle scale. And then we come on into the new millennium, and there's a third edition with Kenichi. And now there is a fourth edition, and I am very lucky to have been invited to be the third author of it. And what you can see, that as time went on, the book got bigger, and if you plot the number of pages against the edition number, it does something like that. And then you can go to Amazon, where I went to get a nice picture of the third edition, and then you can see that the fourth edition will be available in July, and that was news to me, and I just told Kenichi, and we still have a bit of work to do because we haven't proofread the book. So I think that might be Wiley's way of saying, get on with it when we give you the proofs to check. And Wiley give a very nice summary of the book, explaining that it's a generously illustrated resource, and it talks about the properties of soil and soil behavior. And there's an emphasis on projects and problems from the get-go. And my colleague, Jamie Standing, wrote a review of the third edition back almost 20 years ago, and I thought it would be nice to go and look at that when I was preparing for this talk as to how an objective colleague in geotechnics would consider this book. And he says some very nice things, highlighting there was a philosophy about understanding and focusing on particle interactions and soil, water, and chemistry. And then he goes on to say some very nice things about the book in terms of how a reader would interact with it, that it's readable, the references are comprehensive, he values the questions, and that it's a unique contribution to the field of soil mechanics in terms of the depth and the breadth of material that is covered in it. So when I think of the book myself, I think of it as being something that distills research from our own field and other fields, and there was a discussion about whiskey earlier on, so this is a distillery in West Cork, and in case you don't know, I'm Irish, so... and it signposts key references, again, Irish signpost, but I think this is incredibly valuable, and it enables further basic and more applied research. And one thing that strikes me when I come here, people talk about graduate classes. In many parts of the world, people are doing research, and there is not a graduate taught program in their university. So they are relying on resources such as this text to get up and going in their doctoral research. And when Rudy was interviewing Jim, and in his introduction, he summarized quite clearly what it is. So I don't know if you're familiar with this, but this is a very useful figure to use to explain that we are very important as a field, and it's really, really useful when you go to do outreach with grade school children to say, I'm going to present something very complicated, but you can relate to it because it's sand. But Jim himself said the challenge around sand or soil behavior is that there are many fascinating but also purely understood phenomena. And what Jim has done in terms of leading this book is to open up this idea that we can look at things at a very fundamental level. And I think there's two main drivers, in my opinion, on this. The first is our innate curiosity. And I went to get some cartoon about curiosity and then realized, well, this would be very appropriate when we're talking about Jim's contributions, because this rover is called Curiosity. And also, we want to look at things that have societal, economic, and environmental impact. And obviously, particularly in Europe, we're really looking at offshore wind, and there are many geotechnical challenges associated with that. And again, going back to Jamie Standing's review, he really focused on the idea that we can go deep into soil mechanics to look at some very, very important problems. And again, one of the things he really honed in on was the contribution to soil chemistry and the chemical mechanical coupling in the text, and focusing on this idea that it's particularly important when we're looking at contaminated and radioactive waste. And I think we'll hear more about that later this morning. Now, about 18 months ago, I was asked to contribute to a discussion on the Geotechnique Journal and take a look at why fundamental research is important in geotechnical engineering. And that gave me the opportunity or the motivation to go and look at a high level about why, as engineers, do we want to look at fundamental research. And there are some very interesting discussions, many of which come out of the US, on thinking about why governments should fund basic research and fundamental research. And there is a case to be made at a philosophical level about this. It makes applied innovation more productive. It allows new products and processes to be developed. And this is something that can be quite difficult to quantify and to really understand what the long-term impact of this research on society as a whole. They make some very nice statements, but they don't necessarily back these up with evidence. But I think Jim, in his contributions, has actually lived this aspiration. And again, thinking about his interview with Rhode, he says that in a very nice way, saying he did all this work on the very fundamentals of soil-particle interaction and soil chemistry, and he did not realize at the time how important that was going to be. And I think it's very nice because I had the opportunity, because I have very bad jet lag, to listen to that interview again over the past few days. And I thought it was really nice that we have an engineer who worked on practical problems articulating what has been said in these very high-level documents that I've just referred to. And I'm going to give a couple of examples as to why I think the textbook is so important. And the first thing I'm going to do is to talk about Chapter 6. Now, in Chapter 6, Jim, and then later with Kenichi, lay out the explanation for how colloidal particles interact. And they draw in colloidal science and then apply that to think about the interactions of clay platelets. And in the field of particulate soil mechanics, we're now starting to see a transition from DEM simulations on sand to start to look at how can we simulate clay at the particle scale and look at the mechanical response that emerges from particle simulations. And these are some simulations from one of my students. And once you go into that literature, and this what I think is very much an emerging field, you see these contributions from Chapter 6 cited over and over again. And it's rare that you see a textbook cited to such a great extent in scientific research. And for me, I think that's very important because the coupling of different phenomena in soil is one of the challenges that we have in geotechnical engineering. How do we account for that in our design? How do we account for it in our predictive analysis that underlie the design? And we can take a specific example. If we want to develop a new technology to handle swelling soils, Keller have been looking at injecting salt solutions into soil, and this is an aerial view of a test site in the Netherlands. But I think in the book you can see that Jim can go from this consideration of ions interacting with the surface of a clay particle towards looking at field scale applications. The second chapter I would like to focus on is Chapter 9, and that's because for 20 years I've been teaching a class on seepage and consolidation. And also, when we started to look at the 4th edition, one of the things I was suggesting to Jim is maybe we should take the material on temperature out of this chapter and bring it to the new chapter on temperature. But Jim was quite calmly adamant that we needed to keep all of these phenomena together. And as we worked through the book more, I could really appreciate that this is very nice. He takes water flow, heat flow, electrical flow, and chemical flow, and looks at them in that chapter in a unified way. And I don't know any other reference that's widely read in geotechnical engineering that does this. And he goes from these equations at the beginning of the chapter and builds it up towards looking at a general theory in section 9.10, and then moving more towards consideration of applications towards the end of the chapter. And again, this is very, very important in the context of thinking about coupling and prediction of coupled effects in geotechnical engineering. And another thing I really value about Chapter 9 is the way it brings us back into the fundamentals of the flow of water through soil. He starts off by talking about flow in a capillary tube. We have the Poiseuille equation. Then he goes through, in a very nice way, explaining how we can go from the Poiseuille equation up towards looking at a system. And at the moment, I'm engaged with, in some research looking at polymer support fluids. So the idea here is you have an excavation, you put in a casing, you put some polymer fluid here, and it can support the surrounding ground. But the mechanics of this are very complicated, and we don't quite understand how we should design or specify these systems to get the right pressure loss adjacent to the excavation. And it's complicated because our viscosity is changing with our pressure gradient. And as we try to unravel this puzzle, we're going back again and again to think about these fundamentals, to think about the link between the intrinsic properties of a porous media and the effective hydraulic conductivity. So then moving on to the 4th edition, I don't know if you can remember where you were in December 2020. We had the joy in the UK of Boris Johnson cancelling Christmas, so it wasn't exactly the best month ever. And somehow in the middle of this chaos, I got an unexpected email from Kenichi, who announced that himself and Jim were looking at putting together the 4th edition of the textbook, and would I be interested in getting involved? And of course I was interested. I needed to get a bit of permission from my husband because I knew this might have some broader implications, and he was quite happy for me to go along with this because he thought it sounded interesting. And so we went ahead early in 2021 and signed a contract with Wiley. And I went back through my emails recently to try to find the contract because, that was a piece of paper. I wasn't really that bothered about it. It was the work that was more relevant to me. And I could see that back in 2021, we had a bit of deadline movement. And somehow we converged on submitting it at the end of 2022. And we actually submitted the files to Wiley last August. So, but listening to the interview between Jim and Rudy, the 1st edition was also late. And recently I've had the privilege of reading this book. It's by an academic whose name I'm not even going to begin to try to pronounce, who works in Oxford. And he looks at project management, and he looks at this from a very, very big scale. And he talks about big infrastructure projects, but he also includes in his list of mega projects books. And he comes up with this iron law of project management. And in this, we have all projects at 100%. And if we do the very simple addition here, we will see that only 9% of big projects are delivered on time. So we are with the majority of people who are late on projects like this. And I think then we can think about why we might be late. Well, Boris Johnson also closed the schools, so we had homeschooling in 2021. We had teaching, and this is distance teaching under COVID conditions in the lab, and the students were supposed to be 2 meters apart. They did wear their masks, but the minute I went up on the table to take a photograph of them, they were like little magnets, and they all came together. And anytime I did any teaching then, that's what happened. So we had a bit more of an overhead than usual. We had, or at least I had journals to edit, papers to write, grants to apply for. So all of this was going on at the same time in the book, as well as whatever administrative jobs Imperial was throwing at me. So it was hard to find the time to actually look at this new material. And I think Kenichi could have a slightly different story, but similar circumstances. Our day jobs were really demanding. And I think it was wonderful working with Jim because he led by example, always focusing on our commitment to deliver. We would meet every week. Jim had always done the work that he agreed to do at the beginning of the week. We mostly hadn't completely done it. And, you know, I have to say, I always came away from those calls feeling grateful because he was so patient, but yet, you know, constantly reminding us, you know, there is a deadline somewhere out there, even though it moves. So how did we do this? We used modern technology. Box, we had a file on Box where we'd put our updated, our folder on Box where we put our updated files, and we met every week on Microsoft Teams. And the vast majority of my interactions with Jim looked like this. I was at a computer screen, and Jim was sitting in his office in Western Massachusetts, and we were talking, and we had a standing arrangement to talk on what was Thursday evening for me, but we were across 3 different time zones. And we started off by making a spreadsheet of what was in the 3rd edition, and then thinking about how we might rearrange the order of the material in maybe what seemed like a slightly more logical way in the 4th edition. And then we came up with tables of contents for the various chapters, and somebody was in charge of each chapter, and we started to edit the chapters of the 3rd edition to deliver this new format. So again, if we go back to Jamie Standing's review, something similar happened as we moved from the 2nd to the 3rd. We had an increase in the number of pages. We had a change in the order of presentation, and there was some new material in the book. So going from the 3rd to the 4th, we had this increase in the number of pages, and then we had a massive increase in the number of figures. So that required careful management in terms of looking at copyright permission, redrawing figures that were not so clear. So that actually took an enormous amount of time. So we've changed the order of presentation. We've retained most of the original content. There's an additional chapter. There's lots more pages. And we had vowed that we wouldn't do that, but somehow maybe we were just too excited or unable to make tough decisions, but it's going to be big. And just to give you a flavor of what we did, chapter 6 has been moved to be earlier in the book, and the name is the same. Chapter 8, when we looked at it, had a lot of overlap or linked quite a bit with what was in chapter 2. So we took quite a lot of the material out of chapter 8 and brought it back into chapter 2. And this really focuses on geology, and hopefully that makes a more logical flow. Then there's a chapter 11, which catches maybe some of the other items that was in chapter 8 and also keeps chapter 10 from being an unmanageable beast. And I know Jim spent, a couple of minutes trying to think about what could we call this, and I think the title he came up with is very nice, and hopefully you will see it appropriate when you see the actual 4th edition. We have our new chapter on thermal effects on soil behavior. And what's important to appreciate is that advanced drafts of all of these chapters were completed by December 2023. So Jim was well aware of the structure, well aware of the content of these chapters. So after December 2023, Kenichi and I had a large number of Word documents to go through with comments from Jim that we did our best to address, even though, obviously we could never have the conversations with him about, is this what you had really wanted? As well as managing, as I said already, the tough work with looking at the figures. So just to conclude, Fernando Patino, who's now in Georgia Tech, he was working with me for a few years at Imperial, and he came up with this idea of using some of the available tools for text mining that we now have in data science to look at what is the kind of geotechnical engineering research at the moment. And he looked over a period of 25 years at papers that have been published in geotechnical engineering journal articles, looking at the abstract and the titles and the keywords. And these are, in order of popularity, the topics that have been considered. And you can see that soil behavior is at the top. But if you look at the growth or the change in activity, we can see that soil behavior is further down the bottom. Other topics, such as data science, are maybe emerging as the big thing in our field. And I think that's something to discuss. How do we ensure that we keep research in this fundamental areas so that we maintain the knowledge base, we maintain the skill set needed to look at interesting problems such as those that Chris has just put forward to us. So I think, setting aside any of Jim's research, the fact that he, over a period of more than 50 years, curated this book, saw it through different editions, and was so open to including new materials and new ideas and keeping it current, I think is remarkable. I'm sure that if we look across all of the scientific and humanities disciplines, this is very, very rare. And he said in his interview, it was a labor of love, and I think it really was. I mean, his commitment to this project was really, really outstanding. And I think I would just finally like to thank two people who are here today, and that is Kenichi and Holly. In the summer of 2022, Kenichi and I went to stay. I stayed with a neighbor, and Kenichi stayed with Jim and Holly, and we spent 2 very nice days with Jim, and that's the only time I actually met him in person. And that was a very nice opportunity, and it was very, very important. Face-to-face interactions are crucial for working relationships. And I also must thank Holly, because I'm sure she had to absorb some of Jim's inevitable frustrations when we were always late on meeting whatever intermediate deadlines had been set for us to address by Jim. So thank you for your time, and I look forward to talking to some of you later on today.